So we can look at a graph and learn a bunch of stuff about the different wave properties. Here's some more conceptual questions. So a student sends a wave pulse down a rope as shown in the diagram. At the instant shown in the lower part of the diagram, what direction is point A moving? What about point B? So what kind of wave is this? Well, it's a transverse wave because the rope is going up and down. If you think about what's happening, so as the student raises this and then raises the rope, the wave is going up and down. So as the student raises and lowers the rope. So a given point on the rope is going either up or down. Now if we think about point B, well, a second ago, or a short time ago, point B was not displaced. And a short time from now, it'll be at maximum displacement. So point B is going upward. It's moving upward. Even though the wave is traveling in this direction, remember the particles on the rope do not move horizontally. Meanwhile, point A, if we go back in time a bit, it was at max displacement, and now it's going back to zero displacement. So point A is moving downward. So keep in mind, for a transverse wave, the points only move perpendicular to the direction the wave is traveling. So the wave is traveling to the right, points only move up and down. Okay. For number 3, I'd like you to pause the video and see if you can take your shot at each of them and then unpause and see if you're right. So we want to think about each of these and decide whether transverse or longitudinal is a better description. Well, remember, transverse, the wave moves in one direction, displacement is perpendicular to that. Longitudinal, wave moves in one direction, the displacement is in that direction. So we've got a line of people waiting for the train. Someone accidentally bumps into the person at the end of the line, who then runs into the person in front of him, and so on up to the front of the line, and then each person steps back to his original position. Well, so you got all these people. I'm only going to draw 3 people for the sake of time. But this guy bumps into the guy in front of him, so he moves forward, but then he steps back to his original position. So, and then that travels down this way. So the direction the wave is moving is that way, and then people are going that way and back, which is parallel to the direction the wave is traveling. So this is a longitudinal sort of wave pulse. The wave, you've probably heard of. It's something that's done at sporting events. I don't really know why, but you know, people in one area put their arms up, and then people in the next area over put their arms up as the first people put their arms back down, and you go around the stadium making that motion. So if you've got the stands, over here people have their arms up, people here have their arms down, then later on they put their arms up, and then these guys put their arms up, etc. So this wave is traveling through the stadium that way while people are moving up and down. So that displacement is perpendicular to the motion of the wave. This is a transverse wave. This you've probably seen, you know, the dance move where you let a wave roll up one arm and down the other. That's one thing I wish I could do. Although I haven't tried hard, I don't care that much because I haven't tried to work at it very hard. But again, so the wave is traveling down, up and down the length of their arm. So you got the, person's arms, and the wave kind of goes, rolls up this arm and down that way. So the wave is traveling that way, but their arm is moving up and down, which is perpendicular to that. So that is a transverse wave. A wave traveling toward the ocean shore, well, if you've ever been to the ocean or even seen pictures of it, you know that waves go up while they're traveling horizontally. So that is transverse, but this is kind of a trick question because in a wave the water also compresses and then uncompresses. So water waves are in fact both transverse and longitudinal at the same time. They have displacement in both directions. So water waves are both. I wouldn't have expected you to know that on your own. You probably would have, if you were thinking about it, you probably would have said transverse because you've seen them go up. Yeah. So waves on a string or rope particularly, there are two things that affect the wave speed. The first one, you'll know if you have played a string instrument, you know that, well, you might not think about it directly, but it is the wave speed is closely related to frequency, which is related to how it sounds. And there's something you do to change the sound of a particular string, either tighten it or loosen it. So the tension in the string or rope affects wave speed. And again, if the wave is tauter, if the string is tauter, the wave will travel faster down it. If you've ever held a string or a rope, you can try this. If you hold a string or a rope and don't hold it tight, you can't get a wave to travel down it at all. If it is not taut, so it's just hanging there, the wave will stop. It dissipates before it gets anywhere. And then there's another thing that you might not think about, but is related to Newton's second law. In order to move a chunk of rope or string or whatever, you need to accelerate it up and then back down. And in order to, so what will slow down or speed up acceleration? Well, it's the mass. But you're only moving one section of rope at a time, so it's not just the mass, but it is the kind of the mass density or the mass per length of the rope. If there's more mass, the wave will travel more slowly because it's harder for the particles in the rope to move. Mass per length, for brilliant reasons, is often represented with the Greek letter mu. So it's not just the coefficient of friction, it's also mass per length. I guess somebody decided that mass per length and coefficient of friction weren't going to be used at the same time. So those are the two things that affect wave speed. And in doing experimentation shows that they're both square rooty things. And it just happens that the speed of a wave moving down a rope is equal to square root of f over mu. So as in this case, f is tension, mu is mass per length. I figure they use f for tension instead of t because t is already, capital T already represents the period when we're talking about waves. So in this case, it makes more sense to use f for tension. So if as the mass per length gets bigger, velocity gets smaller. As tension gets higher, velocity gets bigger. So we got a horizontal rope pulling a crate of mass 35 kilograms across the floor at a constant speed. The coefficient of kinetic friction between the crate and the floor is 0.22. Rope is 1.5 meters long and has a mass of 0.85 kilograms. What is the speed of a wave on this rope? So just after I got through telling you, somebody decided that you wouldn't use coefficient of friction and mu in the same problem. I decided to use coefficient of friction and mu in the same problem. Or coefficient of friction and mass per length. So, well, horizontal rope pulling the crate across the floor at constant speed. If we apply Newton's second law, crate, rope, what forces are acting? We've got tension, gravity, kinetic friction, normal force. In the vertical direction, we learned normal force is equal to mg, going at constant speed, so tension is equal to kinetic friction. So we can say that the tension in the rope, and actually I'll call it F sub t because we're going to call it F in this formula. So the tension in the rope is equal to kinetic friction, which is equal to coefficient of kinetic friction times normal force, and in this case, normal force is equal to mg. The mass per length, we can just take the mass and divide by the length, and we'll get the mass per length. I guess to be totally accurate, I should have said that the rope is uniform. the mass is uniformly distributed, if I was going to be 100% accurate in my problem statement. So what's the speed of a wave in this rope? Well, it's equal to square root of f, which is equal to mu k m g, and this is referring to the mass of the crate. This is the mass per length of the rope. So the rope has mass 0.85 and its length is 1.5. So we can plug that into our calculators to solve for the wave speed in this rope. 0.22 times 35 times 9.8 divided by 0.85 over 1.5, parentheses, parentheses. We get the speed of a wave in this rope is about 11.54 meters per second. Okay. Then a wave train is produced in such a way that the rope has a maximum positive displacement every 0.85 seconds. So what is that? Well, that's the period. So frequency is equal to 1 over period. So that's 1 over 0.85, which I punch into my calculator to find it's about 1.176 hertz. And wavelength, how do we find wavelength? Well, we know velocity is equal to lambda times frequency, therefore wavelength is velocity over frequency, so that's 11.539 whatever divided by 1.17 whatever, and we can then calculate what our wavelength is. I got about 9, oh, that's interesting, 9.81 meters, not related to the acceleration due to gravity. And then this is one other thing, it's kind of a standalone thing that almost every textbook will throw in a basic discussion of waves, but it's not something that is really applied all that often. That when they reach a boundary, wave pulses will reflect, and there are two different ways that this can happen. If this end is tied so that it cannot move, then the wave will flip. So the reflected wave will be inverted, as shown in the diagram over here. If the end is free to slide, so this is saying maybe this is like a metal ring or something. The rope is tied to that, but this ring is free to slide up and down. Then the wave will, the reflected wave will be upright. The displacement will be in the same direction as it was when it was coming in. And that's just, you don't really need to know why that is. It just is. And that's something that you should know. It's possible that it could pop up on the AP exam. That's your homework. I'll see you next class.